In the realm of image generation, significant advancements have been made with the introduction of diffusion models. These models learn to progressively reverse a given image corruption, leading to improved results in various studies. However, it remains unclear what the optimal procedure for corrupting an image is. This work hypothesizes that the optimal corruption procedure minimizes the length of the path taken when corrupting an image towards a given final state. The Fisher metric is proposed for measuring the path length in the space of probability distributions. By computing the shortest path according to this metric, it is shown that it corresponds to a combination of image sharpening and noise deblurring, rather than blurring. This corruption procedure is uniquely determined by the shortest path diffusion, SPD, which improves on strong baselines without hyperparameter tuning and outperforms previous diffusion models based on image blurring. Any small deviation from the shortest path leads to worse performance, suggesting that SPD provides the optimal procedure to corrupt images. This work sheds new light on observations made in recent studies and provides a new approach to improve diffusion models on images and other types of data. Diffusion models have emerged as a powerful tool for image generation, capable of producing high-quality images. A crucial component of these models is the corruption procedure, which significantly impacts the generated image quality. The key to optimal image generation lies in minimizing errors in reversing corruption, thereby ensuring that the corruption procedure is well designed. The authors propose a novel approach, utilizing the shortest path in the space of distributions as the optimal corruption procedure. This method outperforms existing techniques, demonstrating improved image quality. The concept of shortest path is rooted in the idea that the optimal corruption procedure should traverse the most direct route in the distribution space, thereby minimizing errors. The authors also review related work in diffusion models, highlighting the importance of variance schedules in controlling the corruption process. By adjusting the variance schedule, the corruption process can be fine-tuned, leading to significant improvements in image quality. This research builds upon existing knowledge, providing insights into the optimal design of corruption procedures and their impact on image generation. The proposed approach offers a significant advancement in diffusion models, providing a principled method for minimizing errors in corruption reversal. This research has important implications for the development of high-quality image generation models, with potential applications in computer vision, graphics, and beyond. In the realm of image generation, a novel approach utilizing shortest path diffusion learning has emerged as a promising technique for enhancing performance on image density estimation benchmarks. Unlike previous studies where variance scheduling was determined arbitrarily, this method systematically defines the spatiotemporal properties of the corruption based on the shortest path. This approach introduces image blurring as an alternative corruption method, where higher frequencies are degraded first, resulting in image blurring. However, the choice of corruption in these studies is arbitrary. This work demonstrates that the shortest path corresponds to image sharpening and noise deblurring. Diffusion models can differ in the parametrization of the reverse process, which can be trained to predict either the noise or the original image. While predicting noise results in better performance, recent results suggest that combining both parametrizations may improve image quality. This study uses noise prediction, but other parametrizations can be implemented as well. Recent improvements in diffusion models, such as matrix preconditioning, learning the optimal covariance of the reverse process, and simplifying the expression of the reverse diffusion, can be added to the shortest path diffusion in the future to provide further improvements. Other orthogonal improvements include using orthogonal wavelets to decompose images, replacing the isotropic Gaussian prior with a data-computed distribution, and implementing optimal transport from the data to the target distribution. The shortest path diffusion algorithm is introduced, which computes the shortest path analytically for Gaussian distributions and proposes an application to non-Gaussian cases, particularly natural images. The algorithm and its complexity are discussed, with details of derivations and proofs provided in the appendix. The shortest path for Gaussian distributions is computed by considering an image distributed according to a Gaussian distribution with zero mean and covariance matrix sigma. Shortest path diffusion is a concept in image generation that revolves around the temporal change in covariance sigma t. This sequence of covariances describes a path in the space of probability distributions, with the ultimate goal of finding the shortest path between an initial and a final distribution. To measure path lengths, the Fisher metric is employed due to its connection to the Cramer-Rao theorem and its invariance for reparameterization of probability distributions. A crucial component in diffusion models is the corruption procedure, which is derived by implementing the shortest path. This procedure is designed to initiate from the data distribution and terminate with pure noise, effectively mimicking the shortest path between Gaussian distributions. The approach is demonstrated through equations and examples, underscoring its significance in the context of diffusion models and image generation. By leveraging the shortest path diffusion concept, the paper provides a novel framework for image generation, where the corruption procedure plays a pivotal role. This framework enables the creation of high-quality images by progressively refining the noise distribution until it converges to the target data distribution. The use of the Fisher metric ensures that the path lengths are measured accurately, resulting in a more efficient and effective image generation process. Researchers have developed a novel approach to image generation using shortest path diffusion, which involves corrupting images with a forward process to approximate the shortest path between the distribution of real images and an isotropic Gaussian. This forward process is defined by equations 5 and 6, implying a covariance schedule described by equation 4. Although the true shortest path for non-Gaussian distributions is unknown, the authors hypothesize that this forward process provides a good approximation. To apply this approach to real images, the covariance matrix sigma-0 of the image distribution must be computed. However, this computation can be expensive for high-dimensional images. Fortunately, for translation invariant distributions, the covariance matrix can be expressed as sigma-0 equals FDF, where F is the two-dimensional discrete Fourier transform, DFT, matrix and D is a diagonal matrix with the power spectrum of the data. The eigenvectors of sigma-0 are given by the DFT matrix, and its eigenvalues are given by the power spectrum, which is known to decrease with the squared frequency norm. The authors model the power spectrum using equation 8, which includes parameters C1, C2, and M. They set M equal to 2, following Hyvärinen et al. 2009, and fit C1 and C2 to the empirical power spectrum of the dataset. The power spectrum computed for CIFAR10 and ImageNet 64x64 datasets is shown in Figure 2. The authors present algorithm 1, which implements the shortest path diffusion method. The algorithm computes the power spectrum of the dataset, fits the model parameters, and then iteratively corrupts images in frequency space using equations 12 and 13. The corrupted images are then used to train a neural network to estimate the mapping from the corrupted images to the noise. Notably, the algorithm has a linear complexity in the number of pixels, making it scalable for high-dimensional images, and can be easily extended to larger batch sizes. Image generation using the shortest path diffusion method involves a reverse process operating in frequency space, which is the inverse of the forward process. This algorithm leverages a trained neural network and an optimal filter to produce high-quality images. The process begins with sampling noise, followed by computation of the discrete Fourier transform. The inverse discrete Fourier transform is then iteratively applied to obtain the final image. The effectiveness of this approach is demonstrated through experiments on the CIFAR10 and ImageNet datasets, showcasing improved image quality compared to similar methods. The power spectrum and model fit for both datasets are presented, highlighting the accuracy of the inverse square model. This model accurately captures the underlying frequency distributions, enabling the generation of realistic images. The shortest path diffusion method's strength lies in its ability to model complex frequency spectra, allowing for the synthesis of diverse and realistic images. The optimal filter, derived from the neural network, ensures that the generated images exhibit nuanced textures and patterns. By iteratively applying the inverse discrete Fourier transform, the algorithm effectively inverts the frequency spectrum, resulting in high-quality images that rival those produced by state-of-the-art methods. The experimental results on CIFAR10 and ImageNet datasets underscore the algorithm's capabilities, with notable improvements in image quality and realism. The presented power spectra and model fits provide further evidence of the algorithm's accuracy, demonstrating its potential for a wide range of applications in computer vision and image processing. The image generation process using shortest path diffusion is a novel approach for modeling the corruption process. It begins by analyzing the temporal dynamics of corruption for different frequencies, demonstrating that lower frequencies change earlier, while higher frequencies change later. Figure 3 shows the signal magnitude and noise magnitude plotted against the diffusion steps for both lowest and highest frequencies. The power spectrum of the dataset is computed to obtain the optimal corruption filter. The authors fit the model parameters using least squares regression, resulting in values for CIFAR10 and ImageNet 64x64. These values are used to compute the optimal corruption filter, which follows the inverse square law, a common model of the spectrum of natural images. The optimal filter is applied to investigate how images are affected, observing that lower frequencies dissipate first, and higher frequencies dissipate later, resulting in image sharpening and noise deblurring. This property of the shortest path eliminates the need for arbitrary schedules and hyperoptimization. The training and sampling procedures are outlined, with a slight modification of the codebase and the use of a variant of UNet as the neural network. The parameters are optimized by minimizing the simple loss and using the atom optimizer. The results support the main hypothesis that shortest path diffusion provides the optimal corruption filter for image generation. The authors investigate the effectiveness of shortest path diffusion (SPD) in image generation, focusing on the optimal corruption procedure for producing high-quality images. They hypothesize that the exponent m in the power spectrum of natural images, corresponding to m equals 2, provides the optimal corruption filter. To test this, they corrupt CIFAR10 images using different values of m, resulting in image blurring for negative m, sharpening for positive m, and uniform noising for m equals 0. The Frechet inception distance (FID) metric reveals that image quality deteriorates when deviating from m equals 2, as demonstrated in Figure 4, suggesting that SPD provides the optimal corruption. The authors compare their SPD model with other approaches employing forward noising processes containing blurring or a mixture of blurring and noising. Table 1 shows that SPD outperforms these methods, achieving a lower FID score of 2.74 compared to 4.64 and 3.17 for soft diffusion and blurring diffusion, respectively. The performance of SPD is evaluated across different numbers of total diffusion time steps t in Figure 5, demonstrating that SPD provides good image quality in a wide range of t values and outperforms IDDPM when t is less than or equal to 500. Notably, SPD sharpens images instead of blurring them and provides a more resilient corruption procedure. However, the authors acknowledge that for very large t values, SPD may not offer any advantage due to errors in the reverse process. Overall, the results support the hypothesis that the optimal SPD filter provides the best corruption procedure for generating high-quality images. This paper introduces the concept of shortest path diffusion, SPD, a novel approach to data corruption in diffusion models. Unlike previous studies that explored different corruption procedures and optimized them empirically, SPD provides an optimal corruption method by minimizing the length of the path taken by the corruption in the space of probability distributions. This approach reduces the effect of errors in estimating the reverse transition probabilities and allows for data-dependent corruption, providing flexibility in adjusting the corruption to the given dataset. The authors compare their model with IDDPM and IDDPM plus DDIM, demonstrating that SPD outperforms both models in terms of FID scores, especially at lower values of t. They also show unconditional generation of ImageNet 64x64 images, where SPD achieves better FID scores than IDDPM despite having fewer diffusion steps and training iterations. The paper highlights several potential improvements for future work, such as using dedicated ODE solvers for sampling from the model, more accurate estimation of the covariance of the reverse transition probability, and diffusing in latent space. It also emphasizes that SPD could be applied to other types of data beyond images, although different treatments may be required depending on the data type. The authors present a comprehensive catalog of 35 existing methods for single-image super resolution, categorizing them into three main classes: interpolation-based, reconstruction-based, and learning-based approaches. Interpolation-based methods, including nearest neighbor, bilinear, and bicubic interpolation, operate by estimating missing high-frequency details from low-resolution inputs. Reconstruction-based methods, such as iterative back projection and maximum a posteriori estimation, rely on optimizing objective functions to recover high-resolution images. Learning-based methods, encompassing convolutional neural networks, CNNs, and generative adversarial networks, GANs, leverage large datasets to learn mapping functions between low and high-resolution images. The authors also discuss the evaluation metrics used to assess the performance of these methods, including peak signal-to-noise ratio, PSNR, structural similarity index, SSIM, and visual information fidelity, VIF. Furthermore, they highlight the importance of considering factors such as computational complexity, memory requirements, and scalability when selecting a method for a specific application. The authors then delve into the limitations of existing methods, emphasizing the need for more efficient and effective solutions. They argue that most existing methods are designed for specific scenarios, neglecting the variability of real-world images and the diversity of super-resolution tasks. This motivates the development of a novel, adaptive super-resolution framework that can generalize across different scenarios and applications. Image generation using shortest path diffusion is a rapidly evolving field, built upon foundational works on diffusion models, denoising, and score-based generative modeling. Krzyzewski's pioneering work on learning multiple layers of features from tiny images laid the groundwork for subsequent advancements. Li et al.'s progressive deblurring of diffusion models enabled coarse-to fine image synthesis, while their prior grad approach improved conditional denoising diffusion models with data-dependent adaptive priors. Liu et al.'s DPM solver, a fast-ode solver for diffusion probabilistic model sampling, has further accelerated the development of diffusion-based image generation methods. Ma et al.'s work on accelerating score-based generative models with preconditioned diffusion sampling has also had a significant impact on the field. Nicol et al.'s GLIDE, a text-guided diffusion model for photorealistic image generation and editing, has demonstrated the potential of diffusion models for real-world applications. Additionally, Rissanen et al.'s generative modeling with inverse heat dissipation and Saharia et al.'s photorealistic text-to-image diffusion models with deep language understanding have expanded the scope of diffusion-based image generation. These cumulative efforts have established shortest path diffusion as a powerful tool for image generation, with ongoing research pushing the boundaries of this technology. The concept of image generation through shortest path diffusion, particularly focusing on Gaussian distributions, is a complex and technical topic. A theorem states that the shortest path between two Gaussian distributions with zero mean and covariance matrices sigma 0 and sigma 1, where sigma 1 is non-singular, can be described by the equation sigma t equals sigma 1/2 sigma 0 sigma 1/2, 1t. This equation measures the relative distance traveled along the path, with t representing the proportion of the path traveled. In the special case of sigma 1 being an identity matrix, the eigenvectors of sigma t remain the same as those of sigma 0, while the eigenvalues of sigma t are equal to those of sigma 0 raised to the power of 1t. This implies that the eigenvalues of sigma t satisfy the equation sigma 2y equals sigma 2x alpha, where alpha depends on the eigenvalues at t equals 0. The page also includes a proof for theorem A1, which involves calculating the length of a curve using the sum of its infinitesimal segments. The length of a curve xs in R⁻d, parameterized by a scalar s, is given by the line integral d equals integral s10 ds dx per decisecond, where x, s0, and x, s1, represent the initial and final points of the curve. When using a non-Euclidean, Riemannian, metric tensor I, the length of the curve is calculated as d equals integral s10 ds square root n area summation dxi per decisecond each dxj per decisecond, where each represents the elements of the metric tensor. This content is highly technical and focused on mathematical derivations related to Gaussian distributions and Riemannian geometry, providing detailed insights into the shortest path diffusion method for image generation. The importance of covariance matrices and eigenvalues in determining the path between two distributions is emphasized throughout the discussion. The paper discusses image generation using shortest path diffusion, a method that utilizes the Fisher information matrix as the metric tensor to measure the length of a curve in the space of probability distributions. This approach is reparameterization invariant, meaning it depends only on the distribution itself and not its parameterization. The authors aim to find the curve of shortest length, which satisfies the Euler-Lagrange equation, a fundamental principle in calculus of variations. To solve this problem, they define a Lagrangian function and derive an equation for the stationary points of the Lagrangian, which leads to a second-order differential equation. This equation can be simplified by introducing a new variable t, which is a nonlinear function of S. The solution to this differential equation, with boundary conditions sigma t0 equals sigma 0 and sigma t1 equals sigma 1, will provide the shortest path in the space of probability distributions. The authors also note that the problem can be further simplified by considering congruent transformations, where sigma t equals f sigma t f. This transformation invariance property is crucial for maintaining the generality of the method. The use of the Fisher information matrix as the metric tensor and the derivation of the second-order differential equation are key contributions of this work, as they enable the computation of the shortest path in the space of probability distributions. Image generation using the shortest path diffusion method relies on a non-singular matrix F, which transforms covariance matrices sigma 0 and sigma 1 into diagonal forms through a congruent transformation. This process yields a set of independent scalar equations, enabling the derivation of sigma t, a measure of the relative distance traveled along the path. The forward process is then introduced, where a corrupted vector xt with zero mean and covariance sigma 1 minus t0 is generated. A theorem is presented, which states that the covariance of xt equals sigma 1 minus t0. The proof of this theorem involves rigorous calculations, demonstrating the mathematical foundations of the shortest path diffusion method. This method is employed for image generation, leveraging the shortest path diffusion process to produce high-quality images. The technical underpinnings of this approach are rooted in the mathematical concepts and methodologies presented, providing a robust framework for image generation. The time complexity of computing the power spectrum, a crucial step in the proposed shortest path diffusion method for image generation, is examined. Specifically, the time complexity of the discrete Fourier transform, DFT, and the fit of the power spectrum are analyzed. The results show that the time complexity of DFT is quasi-linear, O, d log, d, and the fit of the power spectrum is linear, O, d, in the number of pixels d. In experiments, computing the constants C1 and C2 for CIFAR10 took only a few minutes, while computing the power spectrum of ImageNet 64 by 64 on a CPU took about 1 hour. Notably, the time required to calculate these hyperparameters is significantly less than the time required for training. The complexity of the power spectrum is not worse than the complexity of training, indicating that the computation time of the former will always be smaller, even for higher resolution datasets. Furthermore, the complexity of DFT scales linearly with the dataset size n, while the complexity of the fit of the power spectrum does not depend on the dataset size. This suggests that the dataset size will not be a limiting factor for the proposed method. Additionally, for larger datasets, an estimate of the power spectrum can be obtained from a subset of the data. The generated images using the proposed shortest path diffusion method are presented in Figure 7. Showcasing examples at t equals 500 diffusion steps for models trained on CIFAR10. The results are compared to those obtained using IDDPM, Nikal and Dhariwal, 2021a, and IDDPM plus DDIM, Song et al., 2021. The Frechet inception distance, FID, scores are reported, with the proposed SPD method achieving an FID score of 2.74, outperforming the other methods. The application of shortest path diffusion for image generation is discussed, showcasing an example of generated images using a model trained on IMOGNet 64 by 64. The model was trained with 1,000 diffusion steps, achieving an FID score of 13.7, indicating a high-quality image generation capability. This approach efficiently generates images by finding the shortest path to the target image in the data distribution, with significant implications for applications requiring high-quality images, such as computer vision and graphics.